So, in this first video, we're just going to cover the very basics of Noether's theorem and the concepts behind it. Now, you may have heard of the conservation of energy. Energy can't be created or destroyed, and this is often assumed knowledge at this point in maths and physics, but you might not know necessarily why this is the case. Here, we'll explore the mathematics behind the most basic assumptions we use in our day-to-day lives about the laws of physics, like how a glass will fall and shatter, and how you assume a ball you kick will end up curling the way you intend into a goal. Today, we'll just look at these very basic assumptions and come up with some laws to explain them. So, have a think for yourself. What equations, laws of motion, physical laws do you know of? Energy is a key one. Energy can't be created or destroyed. Newton's second law, F equals ma. Force equals mass times acceleration. The Suvat equations. And Newton's third law, if object A exerts a force on object B, then object B exerts an equal and opposite force on object A. When I drop this ball, we know that it will fall to the ground, wherever and whenever I decide to drop it. This is due to the laws that govern motion, in this case, acceleration due to gravity. When a ball is projected like this, we can predict its exact trajectory based off the speed that we launch it at and the angle to the horizon we chose. We know that it will not, for example, move like this. The curve will instead satisfy our equation of motion. Turn to this ball being dropped. Now, you may have realised it doesn't matter where or when we drop this ball. It'll fall in the same way if we drop it from the same height and with the same initial force and surrounding conditions, wherever we are in the world or whatever room in the house we're in. Let's say we have a system of two particles like this, both moving around in a circle occupying certain positions. Now, we can move this whole system to a different place in space. Nothing about the physics of our system has changed, but the values of AB and CD will have changed, no matter what time t is. We now have new coordinates, say EF and GH. We call this a translation, and the symmetry here is a translational symmetry. The systems are identical apart from their different positions in space. Now let's say we wanted to rotate this whole system around its centre. While the system has remained in the same place, values of AB and CD at a given time t will still have changed. Again, the system is unaffected by this. This is rotational symmetry. Finally, let's take this system and let it play out for a few seconds. You can see that the particles will move around their trajectories. However, at a certain point, each particle will return to their original positions, and the system will be identical to how it was at the beginning. So, now we've had a little think about this, head to the worksheet and try out section A, just to refresh your knowledge on forces and remind you of the skills you might have learned elsewhere. Now we've done that, let's have a look at a work example. I'm going to just give you a moment to read through this and get to grips with the question. Pause the video here to give yourself a bit of time to have a go at the example. So, first things first, a little sketch of the problem will always help us in this kind of scenario. Now, firstly, let's just sketch the figure of 1.5 meters in height. And then, obviously, it's being thrown from the figure at about shoulder height with an angle of 45 degrees. Now, we can predict that it will take this nice, smooth, quadratic trajectory towards the ground, like this. The point where its vertical velocity is 0 will be right at the top, because the ball is not moving up or down at all in this position. So, true or false? A ball dropped on Earth will take the same time to hit the floor as a ball dropped on the moon from the same height. What do you reckon? False. So, because the gravity force is different on the moon and the Earth, the force on the ball, therefore the time taken to hit the ground, will be different. Okay, great. So hopefully you should now be able to recognise symmetry within the physical world. And when you're comfortable with these two concepts, jump onto PowerPoint 2.